We have a bit time for you to introduce yourself and I will introduce the jurors. So would you like to introduce your team members?
Hello everyone, we are the team force on International Trafalgar Senior High School, and I am the captain Zhong Yixing. They are my teammates Wang Silu, Yu Jiajing, Wu Yizhen. Thank you.
Thank you. So for you, can you introduce yourself? All of us.
Hello everyone, we are available to from Kaohsiung Girls Senior High School. I'm the leader of the team. My name is Wu Youshen. This is Huang Luojia. This is Wu Yizhen. This is Yang Yaojun. This is Wei Yixing. Thank you.
And for you, introduce yourself and your team members.
Good afternoon, everyone. We are Team S601, and this is Benson, this is Benson, this is Felicity, this is Max, and I'm Rick. Thank you.
Thank you very much. And then now I'm introducing you the jurors here today with us, with all of you. I'm Zhang Yuzhen, and this is Guo Zhelai, Zhen Wenjie, Jia Zhida, Li Bohan. Okay, so we'll be the juror for this session. Okay. And then now I think we can start. So the problem available is topic 5 from the. Is that decided already? Okay, then we can start. 先你们的可以自己选题目，真的，最后一场不用跑。Reporter, you can start when you are ready.
Okay. So good afternoon. I'm the reporter of Team S601, and my topic is dancing slinky. This is a problem statement. When a slinky is twisted and its bottom is fixed, We loosen the top closest it to exhibit wave-like motion. What parameters affect the sling's motion and what caused this phenomenon? This is how the phenomenon happens. After twisting the top of the sling, it will trigger the motion of the dancing slinky. So, the principle behind the phenomenon. When applying an additional force onto the top of the sling, the sling will receive an additional force. In order to express the additional force, it will trigger the motion of wave. Because the bottom of the sling is fixed, when the wave arrives at the bottom of the sling, it will reflect, causing a standing wave. It is an extent of conservation of energy, friction, and relative rotation between rings plays a crucial role in this phenomenon. Friction produces X and Y tangential acceleration. So these are the parameters that will be used later. R stands for length of sling's radius, F friction value, L length of the slinky, M mass of the slinky, and K stands for elastic constant. Experimental setup. So this is how I set up the experiment. First, I place a sling here and make its bottom fixed. Then I add an illuminate light here to make the video clearly, and placed in high-speed camera here to catch the motion of the phenomenon. Theoretical model. According to Hooke's law, positions of two adjacent circles differ in their directions by x, y, and z, rotated relative to each other by an angle theta. The elastic potential energy will be this. And the normal force is the weight of all the rings of the specific ring. Ith ring counted from the bottom, so it will be the first ring, the second ring, the third ring. The normal force will equals N minus I multiple mg. Frictional force makes the motions in the x, y, and theta directions are interrelated, resulting in nonlinear motion. If the position vector between ring A and ring B, the vector of location will be the vector location of A minus the vector location of B, and the relative velocity will be the relative angular velocity. So the relative velocity relative to plane will be this. And assuming a frictional force, the frictional force will equals a normal force multiplied the amount of UK, which is this. So this is the model running without frictional force. As you can see, the motion in the x and y directions is synchronized. And in this picture, we know that ring 2 arrived at the top of the slinky the last, and ring 6 arrived at the top of the slinky the earliest. This is the 2D trajectories of rings. The XY trajectory is a straight line rather than the circular path observed in the experiment. In order to make our model closer to the real experiment, we add the frictional force into the model. First, we assume the μk amount is 0.0002, and this is how the x and y directions of the motion. Both of them has a clamps first and wet saver. So the XY trajectory divided slightly from a straight line. This is the model running when the amount of UK is 0.01. So this is the trajectories of rings when the amount is 0.01. The ring follows a trajectory similar to circular motion. So when horizontal offset happens, the motion the sling is will be closer to a circular motion, and the radius will decrease by time. And when the amount of UK is 0.05, it fits the experiment more. Experiment. This is the overview of the experiment. The experiment is divided into two parts. In experiment 1, the independent variables is the materials of the sling and the sizes of the sling. And in experiment 2, the independent variables is the amount of twist return. So this is the experiment process of experiment 1. First, we film the phenomenon. Then we use tracker to analyze. In this picture, I used a scale to measure the wavelength of the sling and the amplitude of the sling. Plus, we use Excel to do the data analysis. This is the experiment process of experiment 2. First, we film the motion on top of the sling. Then we use tracker to analyze to know the cycle of this motion. And last, we use Excel to do the data analysis. This is the experiment 1, effect of different sizes and materials. As you can see, whether the sling is made of plastic or metal, the amplitude decreases while shrinking the size of the sling. Additionally, small plastic provides the most angular velocity and rather than the others. This is the experiment 2, effect of different number of twists. When the sling is made of metal, the amplitude decreases while gaining the turns of the twists, and the angular velocity that 25 turns provides is the most, rather than the 5 and 15 turns in each size. So this is the relationship between the amplitude and radius in two types of material. As you can see, the relation between the radius and the amplitude has a positive correlation. And this is the size, the amount of radius in each size. This is the relationship between the turns and amplitude in different sizes of metal sling, especially when the radius is 4.25, which is the medium metal sling, has a strictly decrease, and the relationship between the turns and amplitude has a negative correlation. Conclusion. As more turns are twisted, the relative angle of rotation increases, causing more energy to be released. A small plastic sling with 25 twists produces the most significant dancing motion. When the material is flat-less as plastic, the smaller the sling, the shorter the cycle duration. A small plastic sling achieves the highest angular velocity after 15 turns. Whether made of plastic or metal, the amplitude decreases as the size of the sling shrinks. And for each size of metal sling, the more it is twisted, the greater the angular velocity it generates, especially in 25 turns. So this is the end of my report. Thank you.
Short question, I want to ask how did you twist the slinky?
Twist the sling, I twist it by my hand.
So do you think that, do you fix the force that you twist the slinky? Or you fix the turns that you twist the slinky?
Because the radius of each sling is different, so the force that we need to twist is different.
So did you fix the twist time?
Yes, I fixed the times of the twist. It's 15. Yes.
And because you use a different material to be your manipulate variable, but I think that it will also affect the mass of the slinky and also the elastic constant of your slinky.
Yeah.
So do you think that it will affect your experiment data?
Yes, it will.
I want to ask that how do you measure your angular velocity?
The angular velocity is measured by calculate because I know the cycle of the sling, so it will be 2 pi
So, but that is about the theory, and I want to ask that
Because you use the external data, how do you get your external data about the angular velocity?
I just calculated it.
Calculate it, so do you use, how can you make sure the angular velocity?
Because first we use tracker to know the cycle, so the angular velocity, because we know the cycle first, so we use 2 pi divide to get the angular velocity.
Yes, but I think that the stinky is 0, right? So what is your define about a term?
What do you mean?
Because the stinky, you know, what's your definition about a term?
One turn.
Good, and then
One turn is like one
rest.
times up.
thank you.
And 3 minutes for turn.
Hello everyone, I'm the opponent Zhong Yixin from Team Photon International Shanghai Girls Senior High School, and today I'm going to oppose the problem number 5, dancing stinky. And there is the problem statement: twist a stinky several times and keep its bottom fixed. After releasing the top, the stinky starts to dance with like phenomenon can be observed from the side view, and explain the phenomenon and investigate the parameter that affect the stinky motion. And I think that I will focus on the trajectory of the dancing stinky. And my main focus is about the motion of the dancing stinky and the reason to the stinky dancing. And there is the review of the report during the presentation about the theoretical model. She used the conversion of the energy and about the wave and the standing wave. And I think that there is a lack of the considering about the energy loss because that she say she considered the friction, but
she didn't put it in her data, and I think that will make an error. And there is a lack of the explanation of the theory. I still cannot know what is her theory connect with this phenomenon. And about the experience data, she used the length and the mass and the coefficient of friction and the radius and the material of the sinky to be her manipulated variables. And I think that's because that about the material, when she changed the material of the sinky, it will also change the mass of the sinky and the density of the sinky and the elastic constant of the sinky. And I think I want to know like how do she think that this parameter will affect the data. And I think that because she used hand, it will make it cause some error. And there is lack of the inner. Okay. And about the data analysis, she measured the circle and the wavelength and the angular velocity and the amplitude about during the dancing process. But I think I didn't know that how was this her data connect with the theory. And I don't know that how the parameter will affect the data and how is the data chain can connect with your theory. And I think that there is a lack of the error bar, and I think that because dancing sinky is not stable, so there may be some chaos or I want to discuss with her that what is the trajectory and the velocity and how your parameter will affect your data. And there's my discussion point about the theoretical model. I want to discuss the energy conversion and the angular momentum conservation and the damping effect, because I think that the friction and the air resistance will also affect the extreme data. And I want to know the main factor to let the sinky dance and the relation between the and about the external and setup. I want to know about the definition of the term, because in the short question, I think she didn't explain it clearly. And I want to conduct the calculation of the elastic coefficient and about the material process, because that you used it in your experiment. So I want to know what is the relationship between your manipulator about the material and your data. And about the data analysis, I also want to know that what is your data change? What do you think that was the reason of the data change? And I want to know the connection between the experiment result conclusion about the sending rate and the existing of the critical volume, because that is not stable. And when we still increase the twist time, will lead to the critical value, and there is all my presentation. Thank you. And I want to invite the reporter to discuss. Can you turn to your data page? Okay, first can we discuss the material, because that you use the different material. So how do you use the plastic and
the
metal to be your manipulator variable, and that is pretty different. And I think that will affect both the mass and the density and the elastic constant together. So
first is about the mass, because we all know that the metal weighs more. So if the mass changes, the frictional force will also change.
yes.
And so it's a connection between both of two, and the other is the elastic potential energy.
So do you make sure the elastic constant?
Yeah.
How do you measure it?
I measure like adding the weight after since I don't put it on the slide.
Okay. So because you say you consider the friction.
Okay.
So
If you have
but I think that because you use the different material of the sinking, so the friction will be not the same. So do you consider it in your experiment?
I didn't add because I didn't calculate the friction in my experiment, because I'm not sure how to calculate the because it's hard to know the amount of the friction.
But I think that because you use the plastic and
and metal to be the two material, and the coefficient of friction of these two things is pretty different. So do you think that will affect your?
Like there's lots of variable in the experiment, so I think we just focus on the variable.
So, but when you change the material, there will be so many relevant parameters will also change. So I want to get your data.
So what do you want to really focus on?
I want to focus on how because you have the data, so I want to know that what the data change. Can you explain this why the data change will?
I think we need to.
You can say it without the kind. You want to stop for a while or you want to use the break? Okay, 我们暂停一下，他们遇到技术性的困难。We stop for a while.
可以侦测到第二个引力，没有办法抓到的。抓得到吗？
还是你们要用这个头，我们的头头看？
没有一下。哦，我看见。
先换一台。
We call for the technical support. See if you can switch the device. 有了。
是刚才是在台风里看到吗？
是这台弄的。他刚刚可能是没有抓到这个。
因为它信号弱的时候一直抓不到。
这边线太长。
这5米线 OK 的，没超过20米，非常可以。
没有，谢谢。Please wait 1 minute. Then the signal comes back. You can continue.
Okay, can you turn to your data page 22? Thank you. Oh, sorry, this page. Yes, this one. I want to know that why don't you have the arrow bar? So, do you have an arrow bar along this experiment, or you just conduct your experiment for the one time?
You mean I should add an error bar onto the chat?
Yes, but because I think that the dancing of the sticky is not stable.
Yeah.
So, do you get you just conduct your experiment one time?
Yeah.
So why don't you get the error bar? So why can't you
This is
find the chat?
the average of the chat.
But I think that will be the because that is not stable. So the experiment data will be different.
So we just didn't add it.
Okay. But I think that
I know what I
should.
should. I know we should do.
I also want to know that because in your data I can see that there is a trend that it will increase, but I cannot know that in the initial it's the radius. Why in the first time that the plastic is bigger than the amplitude of the plastic is bigger than the amplitude of the metal, but about 10 centimeter of the radius this one will be bigger. Can you explain that?
Oh, you mean like at first the plastic is bigger, but when
Yes.
this is smaller? I think it's because, as you know, the plastic is more flexibility. So when it's small, the amplitude will be like when it's small, and I have mentioned that in the conclusion.
So why?
Like that, it provides the most angular velocity.
But
So
the difference between the plastic is bigger than the material. So what do you think that? Because it's because the elastic
it
content
depends
is
on the
different.
size of the sling.
Side of the thing.
The size.
The size.
Yes. Because as you can see, in the slow sling, it may be like the plastic is more obviously, but when it's big, the metal one is more obvious.
So because I think that you mentioned.
I have said that friction plays a crucial role in this phenomenon, and I think you know that the normal force has a high connection with the frictional force, and the mass affect the normal force. So I think it's one of the.
Okay, I got it. So can you connect your data with your theory? Because you mentioned about the energy conversion.
Oh, energy.
And I just see like the chain of your data, but I don't think that can you connect with your theory about energy, because you use the twist terms to be your manipulative variable also, right? So I think that
I know what you mean, but when we're doing the experiment, like I'm not sure how to calculate or make a connection between, because the theory is like an assumption or just a reaction with the principle of the phenomenon.
So I think that you use the twist terms to be your manipulative variable. So what do you think that it will affect which relevant parameters? And I think that the energy will be different, right?
Yeah, energy will be different. So I think it will like affect the elastic potential and.
Okay. Okay. Can we turn to page 24? Next page. Can you tell me why is the reason that this line is flat, relatively flat, and this line is that it will slope?
I think it is the size of it, because I think when the size is medium in the metal sling, it best connect with the conditions that can motivate the
But this one you measure this is the size different. It's not the material different.
I said the size when the size is medium and it is metal. And it
Sorry,
is
it's too small. Can you tell me what is this?
Oh, this is the radius, the amount of the radius. It is H, which is the big sling, and it is made of sling and small sling. If you want to say bigger, is this.
But how do you think that the reason like because this stove is different when one is this stove is very different with this two line.
Yeah. So I said it's like I think when it's because this phenomenon sometimes is changeable. So I think it's like when it's made of the sling is made of metal and when the size is medium, it best connects the need that can motivate the best amplitude.
I still cannot know that what the change, and so I think that this three data trend is that gradually decrease, right?
Yeah.
So why?
So why?
Why do you think that this data will gradually decrease?
It's like because metal sling has less flexibility. So when the choice is high, it can have the best amplitude because it just triggers the like half of the upper half of the sling because it doesn't have that much energy.
did you consider the trajectory of the dancing slinky? Because that the problem statements that we should observe the motion of the slinky.
And so that's why we use like we
I think
draw a
the
dot.
trajectory.
Yes, so we draw a dot on the sling, and then it's easier for us to use tractor to like.
So can you show me the trajectory of the slinky? Trajectory.
The trajectory on this presentation is the assumption. It's running by the code.
So do you think that the trajectory was?
If you want to see the trajectory, I can show you.
I just want to.
Well, a very nice discussion. So time's
Okay.
up.
About the discussion I still don't know that because she used the material of the slinky to be her manipulator variable. But there is also the relevant parameter like the mass and the density and the I think the important part is the elastic constant is different, and she didn't measure about the elastic constant. And I also asked that because she used the twice terms to be her manipulator variable, but she didn't measure that how much is the elastic potential energy change, but she used the energy conversion to be her theory. So I think that is the important part. And I also think that the trajectory of the dancing of the slinky is important because that the problem statement said this, and I think the dancing of the slinky is not stable. So I also want to support that you should make sure this kind of you should consider its name.
Okay.
Thank you.
Make the summary and then take one of this one. So yeah.
First question is to the opponent. How do you think about the error may be caused by human? For example, use hand to twist the slinky.
Yes, I think I'm
And I want to ask the reporter, how do you make out for this error?
You said the force made by human. I think the force doesn't affect this ground really well.
And how do you make sure that when you twist the slinky, the deflection will fully transform to the whole slinky, not just deflection on the top of it?
Like we can see the motion of the funnel, and it is obviously like when twisted up more than 15 twists, it will trigger all of the sling.
Oh, I see. Thank you. And I want to ask the reporter, what caused the slinky dancing? Because in the problem statement it says the slinky will dance at the side view. And what do you think?
It is. I think the reason that causes dance is an energy transform. Like first, the sling owns the elastic potential energy, and after releasing, it's like it was released by a wave motion. So that's how triggers the sling dance. And what's more, because the button is fixed, so the wave will reflect. That will make it like for a while. It will dance for a while because of the reflect.
And why it is not just a rotation, but it dances at the side view. It is not just a simple rotation. And why?
You mean that? What do you mean it's not simple rotation? You mean there's still other changes or what?
Okay, thank you. And how many variables are there in your experiment?
In experiment 1, there are 2 independent variables, and in experiment 2, there is only 1.
Okay, thank you.
This is a reviewer from variable to speaking. First is the experiment setup. They mention the motion of the slinky dancing, and her theory is releasing energy with reflecting conservation of the energy, friction, and cruise flow. First experiment. They assume a frictional force and model running and smaller size, smaller amplitude. Their conclusion: takes more, angle of rotation increases, more energy releases. And the reversing twisting the slinky with hand will cause error. First, I want to mention the reporter's pros. She has clear explanation, clear correlation between theory and experiment. Good experiment setup, but her counts on clear graphs should explain more about her graphs. Not enough data and persuasive. Too much words, no error bar. The opponent. Pros. Clear explanation, great guidance of the conservation, great organization of the problems. Cons. Spend too long time on the question, should guide the reporter further in the discussion. Next is our discussion. Opponent asks, how do you measure angular velocity? Reporter says, I calculate it, use tracker to know the cycle and calculate it. But reviewer thinks, is there any way that you could conduct an experiment to measure it so it's more accurate? The opponent asks, how do you twist the slinky? Reporter says, the force we need to twist is different for different slinky. Reviewer thinks, in constant force can make sure if all the force is conveyed to the slinky. Opponent asks, what material and will affect the elastic and mass, and measure elastic constant. Reporter answers, a variety material. Mass change, frictional force will change. They didn't put on the slide. Opponent asks, what material will affect the elastic and mass? Measure the elastic constant and friction coefficient difference. Reporter answers, a variety material, and reporter thinks she should probably put the need information onto the slide. Next is our question. Reviewer thinks, how do you think of the error caused by the human? Make sure the influence of the error. Opponent says it will cause error. Reporter says it doesn't influence that much. And our next question is, how many variables in your experiment?
Well, very nice review, but time's up. Okay, so thank you.
Thank you.
So I'm the reporter watching that class now, and I'm going to do the number one. First, concluding remarks report. Comparing the model and the data, effect of the materials and the size, the effect of the parameters is completely explained. Concluding remarks, clarification. The relative parameters that change along the sling is hard to separate. So experiments, we simply consider it as a single parameters that change because of the sling's properties. The hence doesn't matter. We measured the force by the rounds we twisted the sling, and we can confirm this by marking. And what's more, I think that the real crucial force that affect the phenomenon is a frictional force. It gives the it gives there is a relative rotate in x and y direction. So I think the force that we add is just to fix the top of the sling to actually before we release it. It doesn't really matter the experiment. And what's more, the linear of the data is due to energy transition, which is called by science of friction. And I want to explain the phenomenon more. It's like the phenomenon is an energy transform. It's transformed by elastic potential energy into the motion of the wave. And what causes the wave to continue is because the bottom of the sling is fixed. So when the wave reaches the bottom, it will reflect and continue this wave motion. So this is all. Thank you.
Okay, thank you very much. So the questions for the jury.
Questions? This slide.
Go ahead.
Go ahead.
你是客人。
I have a question for the reporter. So I think you define negative, right? How do you define negative of the dance?
Do you mean
How do you define negative?
on that?
Empathy.
Amplitude?
Yeah.
I'll just like the amplitude is because in the motion of the sling there is a period, and when it will like this is like this is the amplitude. This is all the amplitude, and this is the amplitude, and it is 2 times the amplitude. And we use a scale because we know the original radius. So when it's in the tracker, we can use scale to know the real amplitude of the sling.
You use the largest deviation.
Yeah.
Okay.
Okay.
Yes.
May I?
Yeah, sure.
Yeah, it's a very interesting problem, but I have some question about the problem. The first, the problem mentioned, the bottom has to be fixed, right? Then you make terms. Okay. Before you release, what happened to the slinky?
Like the sling is like it was like being
I mean,
touched.
in physical term, in physics, talking about the physics of the slinky.
Of the slinky,
Yeah.
so like it has.
Bottom has to be fixed. Why? And
Because
when you turn,
if we don't fix the bottom, it will swing around. If the bottom is stuck fixed, it
Uh-huh.
may move.
okay, then
I think one of the reasons that we need to fix because that when we twist the slinky, the slinky will storage the elastic potential energy. So I think that is the reason why we need to fix.
okay. How about you?
I think the one side of the slinky should be fixed, not free, because if it is free, it will influence the result very much.
Okay. Do you agree? What do you say? Do you agree?
I think I agree with her, but not her. I agree with the reviewer.
Okay. Okay. Then I will ask the following question. You have traced already, okay? Apparently the physical property of the slinky has somehow changed. At least she said there's a occasionally installed. But what happened when you release? Why they can have this kind of wave?
Before we
happen?
release, the elastic potential energy will change into the motion of the wave.
Okay. How about you? Do you have
I
any answer?
think when you twist the slinky, the radius of the slinky will change, and the shape of the slinky will change. And what makes slinky dancing is this shape change, make the slinky dancing at the side view.
Okay.
I think that because there will be the energy transformation because that it will storage the elastic potential energy, and it will cause the connecting energy to the slinky, so the slinky will dance.
All right, thank you. Any more questions?
Yeah.
No more questions.
No more questions? And then, thank you. Any of you?
Maybe I ask.
Okay,
Yeah, so based on what you discussed, there are two factors, I guess. One is energy loss, right?
Yeah.
And one is refraction.
Yeah.
So my question for three of you, if you pick one, which one is the most important?
Oh, the key factor?
Yeah.
Can you repeat the two factors?
So there are two factors you have discussed. One is energy loss, friction, and the other is because the end is fixed, so there's a refraction of the wave. Right? These are 2 points. And my question for you is, I'm forcing you to pick one. Which one do you think is the most important?
I think the web will more important.
Refraction or wave?
Refraction? Can you?
I think the friction is most important.
Okay.
Actually, it's a reflection.
Refraction.
Yeah.
Okay.
Three of them pick up the refraction.
Two.
Two?
You pick friction.
Who pick up the energy loss? Okay, so.
Thank you.
Thank you. Yeah, that's all
那
for
个
you.
给完分数之后，还可以给他们，
哦，
可以
Okay.
给他们。 就是第五场就给他们那个，
我也不知道。
因为这样比较重要，他们可以学到一点东西。
Yes, that is a very good thing to give, so the new, our young scientists to come.
Afterwards.
Yeah, afterwards. So now, are you ready? Okay, so first for the reporter. To take a photo.
You have to.
Oh, I have to
You have to
read.
read out.
Sorry, 6, 5, 6, 5, 6. Ready? Then for the opponent. Okay, ready? 7, 6, 7, 8, 7. Okay. And the reviewer. 7, 5, 6, 7, 6. Okay.
OK，
So
你们可以给他们一点建议，
yes, sure, we can have
这一个人是三个人。
都可以，
comments. 应该用英文说。
没关系，用中文说，因为是最后，
好，
因为它不会影响到后面的分数
因。为分数已经讲完了。
对。
那老师，你想要给队友们一些建议？
我给一个最简单的建议，因为你们的数据你们看不懂，知道为什么吗？你把你的数据图放出来，下面对，就这张就好。我连横轴的单位都看不懂，不是看不懂，是看不到。然后 reporter 要从那边来看更远，更看不到。
是在做图的时候，贾老师说的非常好。做图的时候，像我们去国际会议做报告啊，那个是一个禁忌，就是你横轴的那些字啊，纵轴的字不清楚的话，下面的观众其实都看不见的。就算想给你很好的 feedback， 都没有办法，因为他看不见你说什么。所以这是一个很重要的科学上的小技巧。
对，这个以后你一定会做得非常好。
对。
自从这次之后。
对，上面所有的字全部都太小了，这个是真的好，所有人。
那个图里面的字都很小，所以。
因为年轻人那个老花，但是年轻人看
他们看得到，我们看不到。
而且我们有时候国际会议是在大的舞台上，底下人很远，这样的字是绝对看不到的，所以这个是需要下一次我们要注意。
我只有想讲这些，因为其他的我都还 OK。
其他就是大家就是讨论的态度其实非常好，就是善用时间。
刚才那个你说的那一组有拿那个粉色，对 就是你拿镭射笔的时候，你如果讲data，你就指着那一点。你如果要一句话的时候，不要随着那一句话走，就指着就好了。当你讲的话跟投影片上面的无关的时候，不要那个红点在这边闪来闪去，你手就放下来。如果你讲的跟上面有关系的时候，不要。
就是简报的技巧，像我们做简报不会去一直在那边甩，底下就眼睛就红了。
OK，好，差不多。
对啊，好，谢谢。